All right, so today we're going to talk about entropy, and we're going to be, when we're done, we're going to be able to work a few basic problems on entropy, but I think you'll kind of get an idea of what entropy is from a thermodynamic perspective, and then we'll talk a little bit about what it means overall, and then you'll be able to work a few problems. So first I'd like to review heat transfer, and then we'll talk about entropy for a heat engine. And then we'll talk about entropy for a phase change, like melting ice and that sort of thing, or evaporating water or whatever. Now, so let's begin. We have this transfer of heat. Q represents heating, heat or heating, and it's a transfer of thermal energy and so we talked about conduction, convection, radiation, and that sort of thing, but I don't want to review that. Mainly what I want to say is that heating can result, in if you add heat to something, you will change its temperature. Depending on the mass and the specific heat capacity, which is the property of the material, you'll raise its temperature. That's one thing you can do. But what we're going to do for this is we are going to transfer heat through by, we have the heat of fusion. And this, I don't know why they call it the heat of fusion. It's the heat required, I guess, to fuse liquid particles into a solid. That's the heat that has to be released. I don't know why they call it fusion, but it's the heat to melt or freeze. You could actually probably think about the heat of freezing, because that's what's happening. It's either going to freeze or unfreeze, which is also known as melting, right? And then, of course, we can have a heat. If I have a certain mass of a liquid, I can vaporize it, or I can condense it the other way around. I have to add heat to vaporize something. I have to release heat to condense it back, go from a gas to a liquid form. Now, in the videos that we've watched on the engine of nature and entropy, there was this quantity that was called entropy. And entropy is a measure of increasing, and it's almost always increasing. When you're dealing with entropy, you're almost always dealing with a change in entropy. So really, I could call this like delta entropy. A change in entropy is really a measure of increasing disorder. Increasing randomness, increasing messiness. And it happens thermodynamically. It happens when there's a flow of heat. And it was illustrated brilliantly in the video we watched on entropy, where we had a set of molecules here, let's say a solid, and it's too bad I can't draw in with animation. But these guys are moving really fast. They're really hot. It's a solid, but they're jiggling around really fast, banging into each other, moving really fast. And if I put that right next to something that's cold, well, these particles of this atom, these atoms, let's say that they're hardly moving at all. They're very cold. Hardly moving at all. It's easy to understand that if I put these up next to each other and they're just moving around randomly, this is hot. You would feel a high temperature here. This is cold. You have a low temperature here. And if you come back in a little while, if you look at all these little dots, I won't draw the whole thing. Maybe it will, I don't know. But now these are moving on average a little bit slower, but these are all moving on average a little bit faster. And so what's happened is that this thermal energy, that is the energy contained in the wiggliness of the molecules, has spread out. Reaching what we call thermal equilibrium. That is, everything is, this part here is the same temperature as this part over here. The jiggliness is no longer flowing, and we say we have heat flowing in this direction. Okay? So starting to make some sense, right? I hope. Now, if you look at the, let's say for a short period of time, the temperature stays fairly constant. We said that the increase in the change in entropy is equal to the heat that flowed. And remember, heat flowing is really a change in energy. It's how much energy got, flowed from one place to another. So you can think of it as a change divided by the temperature that it is flowing, at which that heat was flowing. And so, and this has units of joules per Kelvin. Now, by the way, this ratio only works if this is an absolute temperature scale. And we've only learned one absolute temperature scale in here, that's kelvins, right? So we know that a Kelvin is equal to a degree Celsius plus 273.15 or whatever. But it starts at 0. Actually, you can't get anything to 0 temperature. You can only approach absolute 0. That's because all particles have at least some motion to them. They cannot be absolutely still. And that has to do with quantum mechanics, which maybe some of you will study someday. I hope so. Now, this is how we define entropy. So delta S, let's create a little chart here. We have a change in entropy, which we've defined with delta S, and it has units of joules per Kelvin. Now we have heat flow, or the flow of thermal energy, which I guess we call heat. Okay, Q, that's in joules. And we have temperature. We use capital T to stand for temperature. And this must be in kelvins. You cannot use degrees Celsius. You cannot use Fahrenheit. You have to use a temperature scale that starts at absolute 0. And as far as I know, kelvins is the only one I know of. I'm sure there's somebody else has one, but I don't know what it is. Okay. Now let's look at this for a heat engine. Okay, is everybody done with that? Okay. So let's look at entropy of a heat engine. Suppose you have a heat engine and I'm just going to draw the schematic. This is the hot stuff. And let's say the hot stuff is at a temperature of 800 kelvins. That's probably about right for a lot of internal combustion engines and so on. Let's say the outside environment is 293 kelvins. This is the cool stuff. Now, heat always flows from hot to cool. So we're going to have some heat flowing out of this thing. And this is going to be the heat flowing out of the high temperature. Now, I think that the video we watched, they call this QI because that's the heat going into the heat engine. Same thing. Now it goes into some kind of heat engine. Choo-choo train, Stirling engine, a car, internal combustion. If it's internal combustion, the high temperature is actually inside the cylinder itself with exploding gasoline and oxygen. It gets very hot, in case you haven't noticed. We'll extract a little bit of work out of it, and then we're going to have some heat flowing back in. And this is the heat that flows into the low temperature. I like to call it Q sub L. Well, let's suppose this motor is, or this engine, let's say it's 15% efficient. So the efficiency of the engine is 15%. It only turns 15% of the energy into work. So let's say that we have, we let the engine operate for a while and we figure out somehow we measure how much heat's flowing out of it. Let's say it's 100,000 joules flows. So let's say this is given. Well, let's find A. Let's figure out how much heat was work. How much heat got turned into work, and how much heat got is in the low. So A, what is the work done, and B, what was the heat that flowed into the low temperature source. So let's do that first. So we'll say, well, the efficiency is just equal to the work you get out of it divided by the heat that flowed into the heat engine, the heat out of the high temperature source. So figuring out the work is easy. It's just the efficiency times that heat. And so that's going to be 15%, but we want to write it as a decimal, right? 0.15. And then the heat that flowed in here is 100,000 joules. That was given. So this is how much work we did. 0.15. I think that's pretty easy to figure out. 15,000 joules. That's my answer for part A. Now for part B, well, look, energy is conserved. So the heat that flows out of my high temperature source, the heat that goes in to my heat engine, has to be equal to the energy out of my heat engine, because I can't create or destroy energy with a heat engine. So it's going to be the work plus the heat low. So the heat that flows into the low, right? This is conservation of energy here. So this is going to be the heat that flowed out of the high temperature source into the heat engine minus the work that it actually did. So this is going to be 100,000 joules minus the 15,000 joules of work we did. So the heat that flowed into the low temperature was it, what is that, 85,000 joules. Easy. I hope you see that this is easy. If you understand what the terms mean, it's not hard. Now, part C. What is the change in entropy for the hot stuff? based on our definition of entropy? Well, see, delta S is equal to Q over the temperature. Now this is for the hot stuff, so I'm going to look at the hot stuff. The hot stuff is, well, how much heat flowed? 100,000 joules divided by the temperature at which it's flowing. It's 800 kelvins. Now maybe something's keeping it hot. You know, it's the boiler. You keep shoveling coal into that choo-choo train boiler, keeps it boiling, keeps it at this high temperature. Well, if 100,000 joules flows out of the high temperature at 800 kelvins, we can figure out what the entropy is. So 100,000 divided by 800, and I get 125, and that's joules per Kelvin. But wait a minute. Heat is flowing out of this thing. This thing is losing energy. Heat is flowing out. So really this is negative 100,000. So this is negative entropy. In other words, the entropy of my high temperature source went down. It became more ordered. Okay, we took heat away from it. If you take heat away from something, it becomes its entropy is decreased by this much. Well, now let's figure out the change in entropy for the low. Well, here we gained 85,000 joules. And this happened at a temperature, the room temperature, 293 kelvins. And here we're gaining heat. The environment is gaining heat. So its entropy is going up. And here we get 290, positive 290 joules per Kelvin. So last thing I want to know is, what's my total change in entropy? Well, for part E, I just add these together. So 290 plus negative 125 is 165. So this is my total change in entropy. The T stands for total there. Oh, I'm sorry, I'm off screen. Please let me know when I'm recording if I'm off screen. So this is the change in entropy of the hot stuff. This is the change in entropy of the cool stuff. But the universe overall, if like this is the universe, the entropy of the universe overall increased. This always happens in any closed process. If you close this off, say this is the whole universe right here, no matter what you do, this is going to happen. I mean, the best you can do is make the most efficient heat engine you can and reduce this entropy to something very small. You'll never get to zero entropy change. You'll always increase entropy in a practical sense. Now let's talk about an entropy change when you are going through a phase change. So and I'll probably only have time to do this for melting. You can do it for freezing, it's the reverse process, and you can do it also for vaporizing. Suppose I got a drink. Here's my drink. And I have my magical experimental fluid in here. And I've got a bunch of ice in here. So, the heat is going to flow from the environment like this. So let's say this is room temperature. Let's say it's a warm day. 273 is 0 degrees Celsius. 293 is a nice cool day. Let's say 300 Kelvin. That's kind of a warm, hot, sticky day. 300 kelvins. Temperature out here is 300 kelvins. And the temperature in here is 0 degrees Celsius, right? If that's the melting point of water. And so, but 0 degrees Celsius is 273 kelvins. So the temperature in here, this is temperature of the high, temperature low is, what did we say? What did I just say? It was 273 kelvins. Okay. Now, you know that heat's going to flow from the high temperature environment into the drink. This temperature is going to stay the same. Now, I don't know what kind of room you're in, but if you're in a classroom and you've got an ice drink, you're not going to notice any temperature change of the room, right? The room is going to stay at essentially a constant temperature. So let's make that assumption that the temperature, the environment is big enough where we don't really notice any temperature change. Well, what's the, well, then I could say, all right, well, the mat, you let it sit. Let's say given. And let's say you let it sit and you notice that 200 grams of ice melts. And what do I want to know? Fine. Well, for A, I want to know how much heat was absorbed by the ice to melt that water from the environment into the ice water. And then B, what was the change in entropy of the ice? And C, what was the change in entropy of the environment? I'll put E and B for environment. Well, let's solve it. I only got 4 minutes left, so I got to go quick. Q equals, well, this is easy, right? Mass times the heat of vaporization, or fusion, I'm sorry. So that's 200 grams, that's 0.200 kilograms. And I can't remember the heat of fusion for water. Does anybody have it handy? Come on, I only got 2 minutes left. What did I do with my book? Somebody look it up. Not 279, that's specific heat. The heat of fusion for ice. What is it? You're letting me down, people.
3.34 times 10 to the 5.
Times 10 to the 5. What are the units?
Joules per kilogram.
Joules per what?
Kilogram.
Kilogram, perfect. Okay. So I'm going to assume that's right. Somebody else help me. I trust you. Okay. Hayden Hansen. All right. So point 2 times 3.34 times 10 to the 5 equals a lot. Okay, so 6.68 times 10 to the 4 joules. Now let's figure out, that's for part A. Let's figure out for part B. What was the entropy of the ice? Well, the entropy of the ice is going to be positive because heat is flowing into the ice. That's going to be 6.68 times 10 to the 4 joules divided by the temperature, which is flowing in there, 273 kelvins. Now, let's do that. So I'm going to divide by 273. So its entropy increased by 245 joules per Kelvin. That's my answer. Now, what is the change in entropy for the room? Well, the room was at a higher temperature, but the heat left the room and went in there, so the room lost heat. The room lost 6.68 times 10 to the 4 joules. And we're going to divide that by the room temperature, which was 300 kelvins. So that's 6.68 times 10 to the 4 divided by 300 equals 223 joules per Kelvin. But it's negative. Oh, thank you. But it's negative. Now, if I add these two together, what do I get? 245 minus 223 equals 22. I didn't use a calculator for that. Delta S overall increased. So look, just like a heat engine, look, folks, I got 1 minute, I'm going to use it. When we had a heat engine, I increased the entropy of the universe by using that heat engine. When you melt ice, this is a closed system, like this is the whole universe here. Entropy increased. Entropy always increases in a closed system like this, and you can show it like this. Good luck on those problems. They're just like this one. That is all.